Right. So this is unit 2 now. June 20.
The answer is B.
B. Okay. Two resistors of
Isn't
4 ohms are connected in parallel. So yeah, it's B. It's gonna be B because they are in parallel.
R
So
and
it's
B
gonna be
are
4
over
by 2.
5 plus
2 ohm. Yep. And moving on to the second one. A wave is traveling across the surface of a tank of water. The graph shows how the displacement of water at one position on the surface varies with time. Okay, so this is basically the displacement of a particle going up and down, basically water wave. Which property of the wave cannot be determined using the information from the graph? The amplitude, it can be determined. Okay, this is the amplitude. The frequency, it can also be determined because the time is given to you. Time period is also determined, but the wavelength cannot be determined. A student measures and records 4 values of length of a wire. Okay, these are the 4 values. Which of the following should be recorded as the mean value of the length in centimeters?
We will
Okay.
ignore 41.1. Yeah.
Okay, and then the rest of them. Calculate this, please.
$49.8.
Yep, that's the answer. Moving on. During a scan of an unborn baby, a series of ultrasound pulses are transmitted through the mother's body and the reflected pulses are detected. The duration of each ultrasound pulse is kept as small as possible. Which of the following is the reason for this? Okay, duration of each ultrasound pulse is kept as small as possible. Okay, so basically the idea behind this is that you send ultrasound, they get reflected from that surface and they are detected over here. Okay, but this distance is given to you, let's say is X. So the total distance traveled by the ultrasound is going to be X plus X is 2X. So let's see. So that the large number of pulses can be used. Well, if you keep the duration small, yeah, possibly it can be a possible answer. Let's look at the other options. So that shorter wavelengths of ultrasound can be used, so to enable more detail to be seen or to keep the energy of the ultrasound to a minimum. Okay, so basically they're saying why is the reason, why do we keep the duration of each ultrasound pulse as small as possible?
D could also be a good one.
To
D.
keep the energy of the ultrasound. No, the duration does not have anything to do with the energy. The duration and energy is related to the frequency. Shorter wavelength of ultrasound can be used. Well, shorter wavelength, if you use shorter wavelength, what's the use of using shorter wavelengths? So that larger number of pulses can be used. Well, okay, you might use larger number of pulses, but will that help you out? What's the major reason for using the ultrasound? It's in order to ensure, to check out the detail of the unborn baby, right? The major reason for using this ultrasound, to scan out the baby and see what's going on inside. So the ultrasounds are transmitted and reflected, and then they are detected again. The duration of each ultrasound pulse is kept as small as possible. The ultrasound itself is kept as small as possible. Now see, the idea behind this is the following. If you have a wave, and that wave comes and hits an atom, if it hits the atom, meaning for a smaller period of time, the smaller the wavelength, the greater the detail which is seen. Okay, the detail actually depends upon the smaller the wavelength. Or you could say, keeping this as small as possible, the duration, meaning the time period, is kept as small as possible, means that the frequency is actually increased or large. Okay, so increasing the frequency would again give you more detail of this baby. So this is about the detail. This is correct. Shorter wavelength can be used, but what's the reason for using the shorter wavelength? The reason is to ensure a greater detail. This is also correct that larger pulses can be used, but why do we need to use larger number of pulses? So again, the answer is C. Okay, A and B are not wrong, they are correct, but the best option is C. It gives the answer to the context of the question. Get it?
Yeah.
Okay, moving on. A narrow beam of electrons is passed through a graphite crystal and is then incident on a fluorescent screen. The pattern observed on the screen is shown over here. You've got some electrons, they're passing through the graphite crystals. Okay, if you these are graphite crystal, right? So graphite crystal, Okay, graphite means it's actually carbon, right? And if it is carbon, it might have numerous carbon atoms inside of it. Okay, and now you've got electrons as well, and now electrons are coming here and hitting it. Now, if you look at this pattern over here, does this just look similar to something? It's increasing gradually.
Yeah.
What is it? Meaning a pattern like this is obtained. Okay, not over here, of course, not over here. On a screen which is placed over here, you get this pattern like this. So why do we get this pattern over here? See, a pattern observed on the screen is shown. A narrow beam of electrons are sent over here and then incident on a screen, a fluorescent screen. This is a fluorescent screen. So the electrons come over here as soon as they pass through this, and after passing through this, when they fall on the screen, they give a wide range of pattern. That's because the electron beam's direction has changed, right? The direction has changed. This is diffraction that's occurring.
Yeah.
Okay, diffraction that's occurring.
Constructive and destructive.
Yes, that's why we are getting fringes over here. Constructive and destructive interference is what's causing the fringes to form. So now which of the following conclusions can be made from this pattern? But wait, aren't these electrons, aren't these particles? And diffraction is a wave property, right?
Yeah.
If diffraction is a wave property, so can we say that the electrons at this moment are showing wave property? So electrons at the same time are showing wave property. That means that wave electrons themselves have a dual nature. Okay, this is also a topic actually of A2. You'll study there in more detail, but over here it's just a slight addition of that. Electrons can show dual nature. Okay, they can show wave nature and particle nature as well. So let's see. They are being attracted to the graphite nuclei. Well, they are not actually being attracted over here. They are being scattered by the nuclei. The electrons are being diffracted by the crystal, or they are being refracted by the crystal. The only best option is C. Okay, you don't even need this info to answer this question. You don't need the wave property and stuff. All you need to do is just know the basics of diffraction, and yeah, they are being diffracted. Get it?
Yeah.
Go on. A lamp of an input power of 500 watts illuminates a total surface area of this much. The lamp has an efficiency of this much. What is the radiation flux incident on the surface? Okay, basically they're just asking us the flux. Well, the formula for flux actually means the number of waves which are reaching there. And this is watts per meter squared. Just look at the unit. Watts mean power. Meter squared means area. And the negative means it's in the denominator. So they just want us to calculate the power upon area of this this lamp. So the power which is the input power is 500. What's the output power if the efficiency is 30%? So 30% is equal to output divided by the input times 100, right? Can you get me an answer for the output power? It's going to be 30% of the 500. So 0, 0, 3, 5s are 15. It's going to be 150 watts.
150.
Okay, if 150 watts is the output power and this is your area, can we get the power upon area? It's 150 divided by the 2, which is 75. Should it be A? Definitely it's A. It's A.
Wait, I didn't get this question.
Basically, over here, they're asking, they've given us the input power, and they are saying that now you have a lamp over here, and to that lamp, you give some power, 500 watts. And then that lamp converts that electrical power into light power, into luminous power, okay? And that light falls on a surface.
This is under the intensity of light chapter, right?
This is actually the intensity. Yes, correct. They're asking us to calculate the intensity. In other words, because the units are for intensity. Power per meter squared is the unit of intensity. Okay? So now they're just asking us, what's the intensity of light that's falling on this area of 2 meters squared? So for that, we'll need to see how much power is being thrown on it. That's the power output. And according to this efficiency, is going to be 30% of the original. It's going to be 30% of the original power. So it's how much is it? It's 150 watts. Now, if this is the power that's reaching this area, what's the intensity? It's power upon area. So it's 150 upon 2, 75. Get it?
Yeah.
Diagram shows two copper bars M and N with square cross-sectional areas as shown. This is M, this is N. Okay, this is X and this height is 2X. Two bars are connected end to end in series in a circuit. The drift velocity of electrons is V. Which of the following is the drift velocities in N? Okay, you've got two copper wires. First of all, see, they are made up of the same material. If you remember the formula for drift velocity, do you remember it? Same material. We did it. We did a derivation. Just a second. We did a derivation. Remember NAQV?
Oh, yeah.
NAQV equals I, where N represents the number of charge carriers per unit volume, and this is actually constant for the same material. Okay, constant for a particular material. Okay, it's the number of charge carriers per unit volume. So for that volume, the charge carriers are constant for a certain material. This is the cross-sectional area. This is the charge of a single carrier. In this case, it's electron. And this is the drift velocity, and this is the current. Okay, so if you know this, V is equals to I divided by NAQ, right? Now, in this relationship, this is your drift velocity that you got. They told us that they are connected in series, right? These two bars are connected in series. So we can assume that this is first bar, this is the bar M, and the second bar, this is your N. Okay, and then they're actually of the same length. The length is the same, I think. They told us, okay, they didn't tell us anything about the length. But okay, no problem. These are the wires, okay? These are the bars connected in series to one another to a battery. Okay, now if they are connected in series, what's the value of current across them? Is the current gonna stay constant?
No, it's going to divide.
They are in series, it's gonna be constant.
Oh.
Yes, it's constant. See, they're in series. Assume them to be two resistors, so of course it's constant. See, in series. Got it?
Yeah.
And they are made up of the same material, so the value of N is also constant, right?
Yeah.
And the number of charge, the charge of a single electron is also constant. Like it cannot change. Of course, it's an electron. In both the cases, electrons are flowing, right? Hello?
Yeah.
Okay, so if this is constant, then we can say that this drift velocity is inversely related to the area, right? Inversely related to the cross-sectional area. Okay, so if the drift velocity is inversely related to the cross-sectional area, but we don't have the cross-sectional area, we've got the length, right? No problem, we can convert the area into length. Well, instead we can calculate the areas because they told us they are square. So what's the area of cross-section of this bar, this cross-sectional area? This A represents cross-sectional area, okay? If one side is 2x and the other side is also 2x because it's a square, right? This is 2x, that's 2x. So what's the area of this cross-section? Is it 2x multiplied by 2x? Because it's a square? 4x squared, correct. And for this one, it's just x squared. So if you look at it, the area of N is 4 times greater than the area of M, right? This N is 4 times greater than M. So if the N is 4 times greater than the M, then over here, if the area, we increase the area by 4 times, what will happen to the velocity? Will it decrease by 4 times? They are inverse. So option A should be the answer. Get it?
Yeah.
Okay, this is an important question. Okay, this can also be asked in theory. Now, a lamp is connected to a power supply of potential difference V. The lamp is switched on at time t0. The graph shows how the current through the lamp varies with time. Okay, now for a certain period of time, it increases linearly. Okay, as the time passes, the current increases linearly, and after that particular time, the current falls non-linearly, and then after a certain period of time it becomes constant. This is through a lamp, they've told us. Okay, and power supply of this potential difference is constant V. Now the lamp is switched on and at 0, and this is how it happens. Now data logger is used to measure the current. Which of the following is the reason for using a data logger in this experiment? Data logger just gives you a number, numerical value for the quantity. Okay, so it measures the current in numbers. So what is it? It is more precise. It takes readings in short time interval. It can take readings over long time interval. It can plot a graph. That should be the answer, because data logger will give you the numerical values. But no, wait, that's not the answer. They've given B as the answer. D cannot be correct because a graph can be plotted without using a data logger. Okay, yeah, that's also a reason, a valid reason. D cannot be correct because even without a data logger, you can draw out a graph if you have numbers gotten through that ammeter or different value, or you've calculated the values. So let's see, they told us that we have a lamp, the power supply, the potential difference is V, and current is monitored. Okay, against time. The data logger is used to measure this current. The data logger can take readings in short time intervals. Well, this might be a property of data logger. For that, you'll need to go through the topic of data logger, okay, from the book. Okay, this is a property, that's why it's given, that it takes intervals. It takes, okay, if you look at the time interval over here, it is quite short. 0.2 second cannot be measured using a stopwatch. 0.2 second interval. So yeah, this is actually short. So yeah, even from the graph, it's proved that yeah, data logger, they measure smaller time intervals. Clear? Okay, which of the following is a numerically equal to work done on the lamp in the first 0.16 seconds? Work done. How can we calculate the work done in the first 0.16 seconds? 16, so this is 0.1, 0.12, 14, 16. Until this peak. How can we calculate the work done on this graph? On this, basically, work done by the lamp, or work done on the lamp in the first 0.16 seconds. So work done, what's the formula for work done? Energy is equals to power into time, right? And what's power? Voltage into current into time, right? What's current into time? Well, the current into time is not given over here, but if you calculate the area under the graph, what's the area under the graph? It's half times of current into time, right? Is it half times of current into time?
Yeah.
And when we multiply that by voltage, will that give us the energy? Or will it give us half times of energy? Okay, yeah, we don't need to consider the half. Basically, the area under the graph actually will give us the energy. So when we multiply the area under the graph with the voltage, you'll get your answer. So area under the graph multiplied by the voltage will give you your energy of work done. So voltage into area under the graph, option E. Clear?
Yeah.
Temperature of a negative temperature coefficient resistor is increased. Okay, negative temperature coefficient actually means that.
Wait, we missed a question.
Yes. Okay, the temperature of a negative temperature coefficient resistor is increased. Negative temperature coefficient का क्या मतलब है? As the temperature rises, the resistance has to fall. Now, as its temperature rises, resistance will fall. Which of the following has the greatest impact on the resistance of the thermistor when its temperature is increased? Increased kinetic energy of the conduction electrons, increased lattice vibration, increased number of collisions between them, or increased number of conduction electrons. Well, this is actually a property of a semiconductor, and this is the answer. Well, that's a part of A2 syllabus. Okay, so now a student carried out an investigation using conducting putty. Okay, this is something, this is a conductor basically. Conductant putty is a material that's a good conductor and can be made into different shapes. The student found the conductant putty into cylinders of different sizes. Coins were pushed into the conducting putty at either end so that the crocodile clips could be attached to connect the conducting clips into the circuit. Okay, so this is the setup. So we made a conducting putty of length this much, diameter this much, the resistance of the conducting putty of the resistivity is this much. Easy? Can you calculate it? You've been given the length, you've been given the diameter and the resistivity. Can you calculate the resistance? What formula should I use?
R is equals to the resistivity over resistivity L over D.
A, L over A, not D.
Yeah.
Okay, and what's gonna be the A?
Pi R squared, that's going to be pi D.
Yeah, pi R squared or pi D squared upon 4, same thing. So now this is gonna be pi L upon, sorry, rho L pi D squared, and the 4 will go up. Now just please calculate the answer to this. 4.2 raised to the power of minus 2 times the length is 0.075 divided by the pi multiplied by the diameter, which is 9 raised to the power of minus 3, and this in square outside of it. Okay, so what's the resistance? Can you give me the answer to this?
49.5.
All right, 49.5 ohms. Wait a second, let me, oh yeah, that's the answer. Okay, moving on. Two cylinders of conducting putty are connected in parallel across a battery. The cylinders have the same length but different areas. Explain why the cylinder with the larger area will reach a higher temperature than the other cylinder. Any suggestion?
Because it has more capacity.
More capacity?
Wait, no. I'm sorry.
Okay, this is a circuit given to you. They are connected in parallel. Let's say they are connected to the same voltage supply, of course. Now, they have different cross-sectional areas. Let's say if the cross-sectional area of the diameter is d, so the diameter of this one is 2d. Just assuming the lengths are the same. What's the formula for resistance? Resistance is equal to rho L over A. The rho is constant. The L is also constant. So resistance is inversely related to the area, right?
Yeah.
Now, they're asking us if the cross-sectional area will rise. With a larger cross-sectional area, it will reach a higher temperature than the other cylinder, and explain why. Okay, greater cross-section.
That means we need lesser resistance. That means higher temperature.
Lesser resistance, higher temperature, that's the case of semiconductors, not the conducting pulley. They didn't tell us if this a semiconductor or not. You have to think about this. Lesser resistance has some other
It just
effect
makes
as well.
sense for the area to increase. Oh wait, what? Can you scroll up to the question?
This one?
Yeah. Okay.
Now see, basically if you decrease the resistance, what will be the effect on the current? What will happen to the current? It will increase, right?
Yeah.
If the current increases, then of course temperature will also rise. And why will the temperature rise if the current increases?
Because the resistance decreases.
Yeah, so current increases, so therefore more energy loss over there. This will increase the temperature. Okay, and voltage is constant. Okay. Okay, so let's verify this from the marking scheme as well. Okay, lower resistance, V is constant, so V squared upon R, greater power dissipated. The resistance is low. Yeah, thinking about that question though. There will be resistance is low. Okay, you can even forget the current as well. You can just explain it in terms of power as well. You know that they are in parallel, right? So power is equal to V squared upon R. Parallel means V is constant, isn't it? If V is constant, then that means power is inversely related to the resistance. So if you decrease the resistance, what will happen to the power loss across it? Power loss will rise. So therefore, if the power increases, the power loss across that, or the power dropped across that increases, the temperature will rise. Get it? Get it?
No.
No? All right. So basically think of it this way. You've got resistance. R is equal to rho L upon A. Resistance is
Yeah.
inversely related to cross-sectional area. So now if you increase the area, resistance falls. If the resistance falls, there is a formula for calculation of power dropped across that wire or resistor. Okay, now power dropped across this wire and this wire. We need to calculate that. Power, since they are in parallel, the voltage drop across this one is also V and this one is also V, right? In parallel means the same thing. So power parallel means V squared upon R. If we apply this formula for calculation of the power which is lost across these two wires or these two cylinders, then V is constant. And if V is constant, then power and resistance are inversely related. Over here, we deduce that resistance is falling, right? If the resistance is falling, what will happen to the power loss? Will it rise or not? Will it rise?
Yeah. Yeah, it
Okay.
will rise.
If the power loss rises, if more power is dissipated across this one, then that actually means more heat is generated, and more heat actually means more temperature. Get it now?
Right. Okay.
Right. Okay, this is a pretty simple question, just needs a bit of logic, okay? Now, chemists use flame test to identify the presence of metals in a substance. The substance is heated in a flame and the resultant color of the flame is an indication of the metal which is present. So you heat a substance, gives you a certain color. For instance, if it gives you yellow, you can assume it's sodium. If it gives you intense white flame, you can assume it's magnesium, and so on. Okay, this is a part of chemistry, inorganic chemistry, not physics. Now, going on to the question, some of the energy levels of an atom of a particular metal are shown over here. These are the energy levels. Do you know what energy levels are? Do you remember this term? Are they quantum shells?
Yeah.
Yep, they are the quantum shells, or the orbits in which the electrons are present. Now, energy level, and each of these have a specific energy level, and if you look at it, this quantum shell which is at the lower energy level has the lowest, most negative energy, and the one which is at the highest level has the greatest energy. Okay, although it's zero, but it's greater than the negative value. Okay, so any electron over here will have the greatest energy and any electron over here would have the least energy. An electron in an atom is excited to this energy level. Excited means that electron has been given energy, and yeah, it has risen or it has absorbed energy, okay, to this level. Now the electron then makes a transition to this level, okay, meaning from minus 5.8685 it goes there. Calculate the wavelength of the radiation that would be emitted as a result of this transition. Okay, this is pretty simple. Now let me tell you what's happening over here. You've got an electron at this level. Okay, they told us that it's excited to this level.
It excites to 7.65.
And then it decreases to 7.65, yes.
Or can we say de-excites?
Yeah, de-excites, exactly, de-excites. So if it de-excites, it gives off energy. What is that energy equal to? Will it be the difference in these two energy levels?
Yeah.
So the energy given off is the difference in between them. So to calculate the difference, just do the following: minus 5.85 minus the minus 7.65. So basically it's 7.65 minus 5.85. So what is the answer? 1 point?
8.
8 electron volts. Okay, by the way, this electron volt is also a unit of energy, okay? Now, once you have the energy, there is a formula which is called E is equals to HF
Right.
that we can apply, where F represents the frequency and H is a constant called the Planck's constant. Now, instead of writing HF, I can also modify this formula in this following way. E is equals to HC upon lambda. What have I done? We know that V is equals to F lambda, right?
Yeah.
So F is equals to V upon lambda. V is the
Right.
velocity and lambda is the wavelength. Why have I written C? C is this velocity of light. Okay? Since this is an atom, an electron is being emitted, the radiation emitted is gonna be in the form of electromagnetic radiation. Okay?
Okay.
Hello?
Yes, hello.
Okay, let's continue. E is equal to hc upon lambda can be applied over here, where c represents the velocity of light, lambda represents the wavelength of the emitted radiation that they want us to calculate. H is the Planck's constant and E is the change in energy. So now E is what we've calculated as 1.8 electron volts. So what I would suggest is first convert the electron volts into joules. Well, the conversion factor is the following: 1.6 raised to the power of minus 19
Also, what about
joules.
the formula MC is equals to H over wavelength?
E is equals to mc squared.
Yeah.
That is the formula which is used for calculation of the mass effect or the change in energy in radioactivity. It's not applied over here. That's when mass is being converted to energy, or energy is being converted to mass, not energy into energy.
Okay.
Oh, yeah. Now you've got 1 electron volt is equal to this much joules of energy. So 1.8 electron volts is equal to how many joules of energy? Can you calculate that, please?
Two point eight eight into 10 to the power minus 19.
All right. You've got the total energy over here, the value for E. Now all you need to do is just find out the value for lambda and you'll get your wavelength.
Also, this value 1.6 into 10 to the power minus 19. Do they give this?
Yeah, this is what you should know already, but I think it is given to you in the data sheet. And it's easy, by the way. Don't you know the charge of a single electron? That's the charge of a single electron. See, it's given to you. 1.1 electron volt is this much joules. See,
Okay.
it's given, but you do know the charge of a single electron, do you?
No.
This is the charge of a single electron. Okay. Now, anyways, once you have this energy, just plug it in here, get your value. 2.88 raised to the power of minus 19 is equals to H, which is 6.63 raised to the power of minus 34, multiplied by velocity of light. What's the velocity of light? 3 raised to the power of 8, and divided by lambda. Now get a value for lambda, please. What's the answer?
6.9 into 10 to the power minus 7.
Meters. Okay. That's the answer. So, get it?
Yeah.
And now do you remember this value?
Yeah.
Do not forget it, okay? That's also a charge of a single electron. This is very important. Now explain why substances containing different metals will produce different colors of flames. Okay, substances which have different metals, they'll produce different colors of flames. The colors actually depend upon the frequency or the wavelength of the emitted radiation. So if it depends upon those, what does the frequency or the wavelength depend upon? The frequency of the wavelength depends upon the energy according to the formula E is equals to HF, right? The frequency and energy are interdependent on one another. So if they are interdependent, then the greater the gap in between these two energy levels from which the electron is de-exciting, the greater would be the energy, or the greater would be the energy of the emitted radiation or emitted light, and the greater would be the frequency of that emitted radiation or emitted light. So they're asking us, why are there different colors? Different colors because the frequencies are different. And why are the frequencies different? Because the energies emitted are different, because electrons are de-exciting in between different energy levels and different materials. It's not important that all the materials would have electrons at the same energy level. In some materials, the electrons might be exciting through a smaller energy difference, whereas might be de-exciting through a smaller energy difference, whereas in others they might be de-exciting through a larger energy difference, giving a more energy radiation. Okay, get the basic concept now?
Yeah.
Okay, so that's all you need to write down. So I'll just quickly write it down. So in different materials, the frequencies might be different, or I should start by saying energy. Different materials would have different energy gaps in between the energy levels. Different materials would have different energy gaps between the energy levels, due to which different radiations, due to which different energies emitted, different energies of waves, or different energy emitted radiations, or emitted radiations have different energies. Okay, just phrase it, of emitted radiations. And you know that energy is proportional to frequency. Give reference to E is equals to HF. Therefore, frequency also differs, and the color depends upon the frequency. Get it?
Yeah.
Let's check out the marking scheme as well. Okay, each metal has unique energy levels, meaning different energy levels, and only certain differences in energy levels are possible. Only certain wavelengths are emitted. Well, this kind of gives the same answer which we gave over here. Okay, it's the same thing but different wording. Okay, each metal has different energy levels. Yeah, of course, different metals would have different energy levels, and then only certain differences in energy levels possible, so only certain wavelengths are emitted, or you could say that different wavelengths are emitted due to different energy gaps in between them. Okay, same thing. 13, polarizing filter. Polarizing filters are often used when taking photographs outside, outdoors. Light from the sky is partially plane polarized. A polarizing filter can be placed in front of the camera lens to make the sky appear darker. The intensity of the light transmitted through the polarizing filter is reduced compared to the intensity without the filter as shown. Explain what is meant by the plane polarized light. Do you know the definition of plane polarized light? Plane polarized, first of all, plane polarized actually means the light which has been passed through the polarizer. Okay, and plane polarized means, polarization means vibrations which are in the same direction. So the light waves traveling in a single particular direction is called a polarized light, and plane polarized because it has been passing, it is flowing in a single plane or in a single direction. Okay, so explain what is meant by the plane polarized light. A light in which, light is an electromagnetic radiation, so it is made up of vibrations. It is a wave, so of light in which the vibrations are only in one plane, and light in which the vibrations are in only one plane. And which plane is it? The plane containing the direction of propagation of the wave. I hope you know what a plane is, right?
Yeah.
This, for instance, this is a plane, and let's say if a wave is moving within that plane, then all the vibrations are in this plane only and not going up or down or diagonally or any way other than this plane. Okay. The light from the sky is transmitted through the polarizing filter in the camera. As the polarizing filter is rotated, the intensity transmitted light varies as shown over here. Intensity decreases when it is rotated to 90 degrees. When it is rotated back to 180 degrees, it increases. Then 270 decreases. Then 360 increases. Explain why the intensity of the light transmitted through the filter varies as shown over here. So what happens over here is that this filter, when it is rotated by 90 degrees, it starts absorbing light. Okay, it starts blocking the light because it's a filter, right? It will filter out all those lights, which are all those, actually, think of it this way. This is your filter's plane. Okay, for instance, this is your plane of the filter, and the plane polarized light. Okay, let's assume there are two filters that you have. Okay, just a sec. This is one filter, and there's a second filter that has been rotated by 90 degrees. Okay, this is vertical, this is horizontal. Now, when the light passes through this filter, and let's assume this is also vertical. At first it's vertical. As light passes through this filter, or as the waves pass through the filter, it becomes plane polarized. Okay, it flows in one direction only. And if the second one is also parallel to the first filter, then the light will still flow in the same direction with the same intensity. But what happens here is that as this filters, so what's happening over here, only the wave which is vibrating parallel to the plane of this filter is passing through it, and the rest of the vibrations are absorbed. Meaning, if for instance, if there is a wave which is vibrating this way, it will get absorbed. Okay, it will be blocked. Now over here, the filter that you have, this one, if you rotate it by 90 degrees, or if you rotate any of these two filters by 90 degrees, what it actually does is it actually blocks most of the light flowing, because now its plane of filtration has changed. Okay, it filters out the wavelength which is not in its own plane, meaning it will now only allow the light that is flowing within it, meaning the wave this that was traveling this way, and it will not allow the wave which is traveling vertically to pass through it. Okay, so if this wave which was traveling vertically initially, if it comes here, its intensity will be absorbed at 90 degrees. And then after that, its intensity, when it is rotated back, when it becomes vertical to the initial filter, then it is allowed, and then the same thing continues as the angles are repeated. So you have to write it the following way. And the filter is parallel to the vibrations of light, right? Filter is parallel to the light vibrations what happens? Maximum intensity is allowed to flow. What's the role of a filter? Filter's role, this is actually the role of the filter, to allow only that intensity which is parallel to the plane of the filter itself. If that intensity is not parallel, it will get absorbed. And the more it becomes perpendicular, the greater would be the intensity absorbed. Okay. So now, as the filter is rotated, intensity would change. Okay, it would change because now as the filter gets rotated, it starts becoming it starts becoming perpendicular to the vibrations. Okay, if these were your vibrations, and now the filter has changed its direction and has become perpendicular to the vibrations, it will start absorbing it. So as the filter is rotated, initially when it was not perpendicular. First, it was parallel to the vibrations. Think of it this way. The vibrations are up, down. Okay, so this is also parallel to those vibrations. But now as it starts changing its position, we can consider this filter as a vector. Okay, we can consider this as a vector because the plane can be considered as a vector. So now, because this is an area and area is a vector, so as it changes its position, then only that component of the vector or that component of this area which is parallel to the vibrations will allow the this intensity to pass. The rest of it will absorb it. So we can use the term component of this filter. As the filter is rotated, only a component of the filter allows light to pass, light to be transmitted. Then we could give reference to this minimum intensity as well, which is at the perpendicular. So as the filter becomes perpendicular, it absorbs all the wavelengths. As the filter becomes perpendicular, absorbs most of the intensity. So the transmitted intensity would become minimum at that particular point. And if you look at this graph, is this reaching zero? It's never reaching zero, right? So never reaching zero actually means that it's never completely polarized, meaning this initial light which was coming from the sky, they told us in the question that this light has been, where did they tell us? Okay, right over here, they told us that it has been partially plane polarized. Here it is, right? So the initial light which was coming from the sky had been partially plane polarized. So that actually means, okay, if this light which was passing through the first filter, which is actually the sky itself, if it had been completely polarized, then making another filter or keeping another filter perpendicular to that would have completely blocked the light. Okay, remember that. Whenever two filters are placed perpendicular to one another, then no light is transmitted. Given that the first one is polarizing the wavelength completely. But if the first one partially polarizes it, then the second one, even if it is kept perpendicular to the first filter, it won't completely absorb the light and some of the intensity would be transmitted. Okay, this is a general rule you need to remember, that whenever two filters are there, the first one, if it is placed upright and the second one is placed perpendicular to the first one, then no intensity should pass, given that the first one is polarizing the light completely. But if it is it is partially polarizing the first one is partially polarizing the incoming light, then the second one will not be able to completely block the light. So since the intensity doesn't reach, wait, where did it go? Over here. Since the transmitted intensity never reaches zero, even at 90 degrees, that confirms that the light was never completely polarized, or light is never completely polarized. And this completes the answer. Why are they not darkened? Okay.
Because it's a partially polarized light, as we discussed earlier.
It is partially polarized, but it's from the sky. If you look at the picture, now see, the sky is almost black, but the clouds are still white. The light coming from the sky, they told us, is partially polarized.
So the light coming from the clouds are not polarized at all.
And why are you saying that?
Because they're parallel to the plane of polarization.
Well, it's not polarized because see, it's even if you apply a filter, there is no change in its color. See, the clouds are still as white as that. When you apply a filter at a different angle, meaning as you rotate this filter, then the cloud's color should become darker. But it's not as dark as the sky because its light is less polarized than the sky, or it's not polarized at all. Okay? It's less
Yeah.
polarized would be a more sensible answer because it is turning black after all. See, it is turning black, but slightly. So yeah, that could be a possible answer. And that is actually an answer. Light from the sky is light from the clouds is less polarized as compared to the sky. Okay, we've got an iceberg over here. The beam of light from the sun travels to the top of the layer of the ice and is incident on air bubble. Okay, the diagram shows the path of the two rays of light within the beam, ray A and ray B. All right, you've got this air bubble over here, and you've got these two rays. This is being reflected there, and this is being refracted, and then meaning it has been transmitted, and then it's there you go. You've got the refractive index, and they need the speed of light in ice. What's a formula? Refractive index equals speed of light in medium divided by speed of light in vacuum. Right? You know what the speed of light in vacuum, right? It's 3 raised to the power of 8 meters per second. This needs to be calculated. A refractive index is given to you to get the value for x, which is, can you calculate this please? 3.93 raised to the power of 8 meters per second. Clear?
Yeah.
Okay. No, wait. This isn't the answer. Oh, wait, I put the formula the other way. The reciprocal of the formula is vacuum divided by medium. So not the medium divided by vacuum. Vacuum upon medium. This is actually 3 raised to the power of 8 divided by 1.31, not multiplied with it. Now, get the answer, please. What's the answer to this? .29 raised to the power of 8 meters per second. Clear? Hello?
Yeah.
Clear? Is this question clear?
The basic formula for this was I is equals to C over V.
Yeah, it's C over V.
Okay.
When you're moving from denser medium to lighter medium, the ray could either get refracted or it could get reflected. And this sort of reflection, when you're moving from denser to lighter medium, it's called TIR. Do you remember TIR? Total
Yeah, total internal
internal reflection. And the condition for total internal reflection was that the angle of incidence must become greater than the critical angle, right? Over here, this angle of incidence would be lesser than the critical angle. That's the reason why total internal reflection is not occurring and refraction has occurred. That's why it follows that path. So that's the answer Why does it follow that path? Because the angle of incidence is less than the critical angle. Incidence is less than the critical angle, due to which it gets refracted. Light ray gets refracted. And does it get refracted towards the normal or away from the normal? Away from the normal. Gets refracted away from the normal, because if you look at it, see, this angle has become now larger. So it's the direction, the path has bended, but it has bended away from the normal, not towards the normal. Okay, it has bended away from the normal. Clear? Let's look at the marking
Yeah.
side of it. It is less than the critical angle, so they are refracted away from the normal. Okay, there's a second mark too. Increase in speed from air to iceberg, decrease in refractive index, decrease in optical density. Optical density means the density of the optical medium. It actually is some more or less the same as refractive index, but increase in speed from ice to air also has a mark, so you need to write that out part as well. And yes, definitely that's a true point, because you're moving from denser to lighter medium, the speed has to increase. There's an increase in speed, although it won't be a much it won't be a significant increase, but still there would be an increase in speed from ice to air. Clear? Now ray A is totally internally reflected at the surface. Determine the minimum size of this angle theta. Okay, all we need to do is just find out the minimum size of this angle. Okay, when will total internal reflection occur? When this becomes greater than the critical angle, right? Now, so over here, they have also given us the refractive index of ice, which is in the first part of the question, 1.31. So the refractive index is 1.31. Okay, theta is needed. If you remember the formula, sine I upon sine R equals N. Incidence upon refraction equals the refractive index. In case of critical angle and in case of total internal reflection, we actually reverse the formula. We reciprocate it. So this is gonna become, what's the angle of incidence in this case? Now see, you're moving from ice to air. In case of ice to air, you're moving from denser to lighter medium. This formula is for the other case. This is for the lighter to denser medium. So when you're moving from denser to lighter medium, you reciprocate it, and this 1 upon n, or just forget this. You just use the same formula and get the value. You know that angle of refraction is actually your 90 degrees. So sine of 90. Angle of incidence is your critical angle, and n is there. You need to calculate the value for n. So this needs to be reciprocated when you're moving from a denser to a lighter medium. So it's going to be sine R upon sine I equals n. Now you can apply it. Refracted angle is going to be 90. So sine of 90 is 1, divided by sine of the critical angle is equals to n, which is 1.31. Now find out the value for C. It's going to be sine of 90 is 1. 1 divided by 1.31. Take the sine inverse of it, and you'll get the minimum angle. Can you give me the answer to this? Oh, maximum. Oh, yeah, minimum size of the angle. Sine inverse of 1 upon 1.31 is? Basically, I've written two different formulas for the refractive index. If you look at this formula, it's R upon I. And if you look at this formula, it's I upon R. Why have I done that? Any suggestion?
Because it's denser to lighter, less denser.
Yes, okay. So this one is from lighter to denser, you apply this formula, and when you're moving from denser to lighter, you apply this formula. You basically reciprocate it to get the value for n. Okay, and then since this total internal reflection is occurring when you're moving from denser to lighter, you're going to use this formula and get the value for C. And for it, the refracted angle is going to be 90 degrees because that's how you get the critical angle, which is 50 degrees. 15. The graph shows how the current through a filament lamp varies with the potential difference applied across it. Explain the shape of the graph. Oh, we've done this question yesterday. This is a repeat. What's happening? As the voltage increases, the current increases. But after a certain point, the graph starts becoming parallel to the voltage axis, meaning the rate of increase of current becomes less than the rate of increase in voltage. That's because as the voltage increases, the temperature also rises. And if the temperature rises, the resistance also rises. And if the resistance rises for a filament lamp, okay, this is a case only for a filament lamp, not for a
Yeah.
thermistor, not for a diode. So if the resistance rises, the heat produced will also rise. Sorry, meaning not the heat. Heat has increased already. So if the resistance rises, the current increase in current would become smaller. So that's why this graph starts becoming parallel to the voltage axis. And same goes on the negative side as well. As the voltage increases in the negative direction, as the voltage increases in the negative direction, the current initially increases, but then as the temperature increases, the resistance also increases. So this decreases the rise in current on this side as well. So it's a curve type of, you get a curve, you don't get a straight line because the resistance continuously changes. So let's look at the marking scheme for it because it's a theoretical answer. Okay, it says the current increases, the potential difference increases. We did mention that. Then it says causing the temperature to increase. Okay. Then we said, okay, they increases the lattice vibration. We missed out this point. We need to make sure of this. Then greater rate of collisions between the electrons and atoms increases the resistance. Okay, this is that same band theory. In terms of the band theory, they've given this answer. The rate of increase of current with the potential difference decreases. We've also mentioned this mark. So we got 3 out of 2 because we out of 5 because we missed out these 2 points. So you have to make sure you write these 2 points as well. There's an increase in lattice vibrations due to which increased collisions of electrons with atoms. Okay, so this decreases the rate of increase of current. Okay, decreases the rate of increase of current with the potential difference. Get it?
Yeah.
All right, moving on. Part B says the current potential difference graph for a particular filament lamp is given to you. As the voltage increases, the current increases until it starts curving. Okay, now this is the filament lamp is connected across a battery of 6 volt as shown over here. This is a filament lamp, this is 6 volt battery and it's connected. The voltmeter reading is 4.2 volts. What's the internal resistance of this battery? So let's assume that an internal resistance is going to be a series resistor. Let's say it's R. Okay, now the voltage is given to you is 4.2 volts. What's the voltage drop across the internal resistance? The volts lost across the internal resistance, volts lost in internal resistance are going to be the total minus the 4.2 will give you the volts lost. So it's going to be 6 minus 4.2. Can you give me the answer to this? It's going to be 0.8 and 1 and 1.8 volts. Now once you have this volts lost across that resistor, you can determine what's the internal resistance of that resistance is by determining the current across it first. Now, to determine the current, you can use this graph. Why am I saying that? Well, because you've been given the voltage value as 4.2. To get the corresponding value of current at 4.2. So it's gonna rise up to somewhere over here. If you zoom in, it's gonna go over here, 510 milliampere. The current value is 510 milliampere. this is the total current which is flowing through this circuit. So it is flowing through all of these components. You've got the current, you've got the voltage. Can you get the resistance? R is equals to V upon I using Ohm's law. V is 1.8 and the milli needs to be converted. So can you get me the answer to this, please? Oh, sorry, not ampere, ohms. So it should be 3.53 ohms. Let's verify that as well. Yeah, that's the answer. Then part 2 says, okay, no part 2, question 10. 16, sorry. The quality of sound heard by listeners at concert depends upon the design of the concert hall. Two loudspeakers S1 and S2 are placed over here. This is S1, this is S2. Connected to the same source. Source is the same. This means that they'll produce coherent waves. Remember what coherent is?
Yeah. Wait, sir. I'll be right back.
Okay. Okay, you've got the coherent, these two sources which would be producing coherent waves because they are connected to the same source. Two speakers actually. Now point A is 3.1 meter from the source and this is 4 meter. S1 and S2 emit a frequency of this much. Explain why the sound heard at A will be quiet. Your answer should include calculation. The speed of sound is this much. Quiet, what does quiet means? Constructive or destructive interference?
Constructive, destructive.
Destructive. Destructive interference is occurring over there. So let's look at what's happening. Okay, this is your point A, and this is S1, and they gave us the distance from S1 to point A, which is 3.1 meters. They gave us this distance as well, which is 4 meters. And now once we have the distance in between these two paths, meaning the distance of this path and the distance of this path, can we calculate the path difference? What's the path difference? 4 minus 3.1? The difference in the two lengths, right? It's going to be 0.9 meters. Now, once you have the path difference, can you use it to determine whether it's going to be constructive or destructive? Definitely you can. Now see, if you remember your theory, path difference when it was equal to lambda by 2 or 3 lambda by 2 or 5 lambda by 2 or 7 lambda by 2 and so on, in that case only, destructive interference would occur. Do you remember this from your theory? If not, this is actually the condition. So now the path difference given to us is 0.9 meters and we need to check it in terms of lambda. This is the path difference given to us. Do we know the lambda? We don't know the lambda. So can we calculate the lambda from the frequency and the sound, speed of sound which they have given us? Can we apply V is equals to F lambda to get the value for lambda, which is going to be V upon F? A value for V is 340 divided by the value for frequency is 567. Can we give me the answer to this, please? 340 by 567 is? Should be a nice answer.
0.59, 0.60.
Yes, 60 is better. Now 0.60 is the wavelength. So if one lambda is 0.60 meters, what's 0.9 meters? How many lambdas? Let's calculate that. Use the unitary method. X is equal to 0.9 multiplied by lambda divided by 0.6. What's the answer? Is it 3 upon 2 lambda?
Yeah.
Yes, it is 3 upon 2 lambda. And is 3 upon 2 lambda in this series?
Yeah.
So since the path difference equals 3 upon 2 lambda, therefore the destructive interference has occurred, and so the sound is quiet. Clear?
Yeah.
Part B says, okay, let's look at the marking scheme as well. What they have given. Okay, they've given us the wavelength, and then they've given us the path difference. 3.2 lambda, so destructive, and so zero amplitude. Oh, zero amplitude also has a mark. We lost this mark. So although it's implied, although we know that, but still. Oh wait, yeah, zero amplitude needs to be written as well to get that mark. Okay, the fourth mark is it. 0 amplitude. So do not miss this out. Okay.
Can you show me the whole answer?
Sorry?
Can you show me the whole answer?
Yeah, here it is.
Okay.
Now, you've got the formation of standing waves within the concert hall may also create points where the sound is loud and quiet. Okay, so if you have the stationary waves, then of course you'll have both loud and quiet. Now, two methods used to prevent the formation of standing waves are using soft fabrics on the walls or using tiles placed on the walls at varying angles. It's just how each of these two methods reduces the formation of standing waves. Any suggestion? For standing wave, what is the condition? You must have a reflecting surface, so when it comes, it hits it, it returns back, right? But if you have foam, or if you have fabric, or if you have tiles over here, will the wave be reflected by the same intensity or not? Will some of the wave be absorbed?
Yeah.
Okay, so will the energy reduce?
Yeah.
So will the frequency also reduce, or the intensity also reduce? If the intensity reduces, the wavelength, sorry, not the wavelength, the amplitude actually. The intensity reduces, the amplitude decreases. And if the amplitude decreases, then the forward and the backward waves will not have the same amplitude. Forward and backward, or forward wave and the reflected wave, they'll have different amplitudes. And if their amplitudes differ, then standing waves are prevented, because for standing waves, they must have the same wavelength, type, frequency, everything. Okay, frequency has reduced as well. Verify it. Absorbs energy. Varying angles leads to reflection in a different direction. Oh, varying angles. Okay, we missed out this point as well. You need to learn this. Then, so there is little superposition in between them. To avoid MP3, there needs to be some indication that the answer is referring specifically to soft fabrics or varying angles of tiles. Okay, so little superposition and stuff. So varying angles of tiles, this part, Johanna, we missed out this point. And at varying angles, because the varying angles would cause the reflected sound to be reflected in at other angles. Of course, if you applied them at different angles, it won't allow the sound to be reflected in the same direction, but might cause the sound to be reflected in some other direction. Okay, and this completes the question. We'll continue with question 17 in the next class. Actually, no, not 17, because that's a Doppler effect. It's not a part of your syllabus. Question 18 in the next class, inshallah, meaning tomorrow. And after this is your homework. Okay, the rest of the paper is your homework. We're going to discuss the